Hello, my name is Rez, and I'm a professional game programmer, and I do electrical engineering as a hobby. And this is the Robot Advent Calendar Day 7, and this is going to be an interesting one. But I want to talk about transistors. We have to understand what they are. This is The Art of Electronics by Paul Horowitz and Winfield Hill. It is an excellent, excellent, excellent book on electrical engineering. It's a hardcore book, so I wouldn't recommend it for beginners at all. But I definitely, if you want to get really serious about this, I do recommend it. It's a really good book. Okay, so I want to open to the transistor page, or one of the parts of the transistor chapter, because this is such an amazing image. This diagram of how a transistor works is just fantastic. So a transistor has several leads. Here's the schematic symbol. Looks like that. And sometimes it has a circle, not always. This is the base. We have the emitter, and we have the collector. In general, you're going to have this connected to ground. Now, there may be some circuit or something like that. This is going to be connected to your signal, whatever that is. This is going to be connected to your sort of load. So there'll be some kind of, in our case, this is the motor, for instance. Like it's going to be connected to something. And this is how our circuit works right now, where the signal is just a constant value. So they're used for things like amplification. That's very common. They're used for switching, which is what we're basically doing it. They're used for just amplification, which is, I think, what we're going to end up doing. I think amplification is likely the end result of this transistor because those motors can pull a lot of current, and you need to have, you can't like pull that from a microprocessor. So usually there's some kind of amplification circuit. I think that's where we're going with this. Importantly, this is also a very specific type of transistor. This is an NPN bipolar junction transistor. So it's a very specific type of transistor. There's many different types with different uses, but this is a very common one. The one that they gave us in particular, the BC337, is one of the more common ones. There's a bunch of different types. So that is what we have. Now let's go back to our diagram of Transistor Man. That's what they call him. I love it so much. Okay, let's go through Transistor Man and what he is. So we have our base to emitter junction. So let's go back up here. One thing that I should probably mention here, I think maybe it wasn't super clear, is there's two flows that we're concerned with. There's this flow, which is the base to emitter flow, and there's this flow, which is the collector emitter flow. These are the two current flows that we care about. How things change from base to emitter affects how things change from emitter to collector. Okay, with that, we can look at Transistor Man. So we have emitter to base. You can imagine a transistor as being like a worker sitting inside of this transistor who is watching the current flowing from the base to emitter. It's watching that flow. Based on what that value is, he then changes this internal resistance to change the output current to match with some multiplier. You can see that up here. We have current at the collector equals the HFE. I usually see it written as beta, but HFE, they're interchangeable. This is our gain of the transistor itself. It's an internal value and not a consistent value, multiplied by the current at the base. So basically we take current at the base, multiply it by a magic value, and we get our current at the collector. And this guy determines how that happens, that magic value. So we're essentially changing this resistance. Now, you can't think of this as a resistor. It's a funky and fancy component. And to give you an idea of what that looks like, these are some actual values here. These are fairly typical values. So here we have, along the x-axis, we have the current at the collector in milliamps. So from 5 milliamps up to 500 milliamps. Here we have the DC current gain, the beta or the HFE. And so as you can see, these curves change, and they change at fairly different temperatures. So at negative 55C, this is our gain. 25C, which is what you typically see, this is our gain. But as we get here to 125C, the gain changes. So the gain is changing based on temperature. It's also changing based on how much current you're pulling from the collector. That's going to change as well. So this beta value is going to change. And yes, that means you can get some really crazy things happening. For example, as a transistor is heating up, we can see that as temperature is going up, our gain is going up. Our overall beta is going up, which means that it's going to draw more current, which means it's going to heat up more, which means it's going to go even further. And you can get this sort of runaway current. And that's how transistors can burn out. Now, a well-designed circuit is not going to do that, of course, but if you're engineering a circuit, you have to account for, well, how hot is this thing going to actually get, right? It has to stabilize at some point. But yeah, as it gets hotter, things very much change. And so here's another really good example of a transistor circuit actually happening. We have this 3.3 volt signal, and this is a square wave, so this is just going to go on, off, on, off, on, off through this resistor here. So we're drawing a bit of a current here, which is causing a much greater current to flow through here and light up this light. That's the idea. That's the core of what we're trying to do and what a transistor is essentially doing. And there's many different ways you can hook it up. Here's another schematic down here that shows just another way where you can turn things on with a lower value. It just depends on what you're trying to do. And this is a datasheet that I found for the BCC337. It's actually for multiple different variants of this, but that's not uncommon. And we can look through all this stuff and find out like maximum characteristics and all that stuff. But there's a few things that we're interested in. Let me scroll down here to this, the DC current gain. So this is our actual curve that we care about. So based on the collector current, we can determine what the gain is, how much we're doing this multiplication. Now it assumes that voltage at collector is about a volt, or from collector to emitter is about a volt, and that we're at about 25 degrees C. And so this gives us a nice little curve that shows us about what we're going to get. We're going to average around 100. So in other words, if we have about 5 milliamps on the base, we can expect that we could get in the upwards of 500 milliamps on the collector. Of course, this is all going to be based on a number of different things, such as resistance and all of that stuff. Now, if you're curious a little more of what's going on the atomic level, well, you have these atoms, silicon atoms, and by themselves they're not great at conducting electricity. But what we do is we do what's called doping, and we create two types of materials. We have a P type and we have an N type, depending on what we dope it with. So what does this do? Well, it biases like what direction current can flow. Like I said, I'm simplifying this, but if we create this basic junction where we smash these two things together, this P and N junction, you can think of the N junction as kind of having little free electrons that are kind of hanging around. It doesn't technically have a negative charge because the doping material still balances out with the protons and the neutrons, so there's no charge here, but there are these free floating sort of electrons that can bounce around between the valence shells of the others. Much like on this side, we have holes, which I'm just going to mark as pluses, but sort of not really missing electrons, but effectively from a silicon point of view, these holes where electrons want to go. Now, if we apply current going in this, or voltage, a positive voltage here, and ground, we have a positive differential like this, these electrons are going to have a place to go. So this is going to be a positive field. It's going to try and pull these electrons in. Now, you have to have enough of a voltage to pull these guys over here. There's a breakdown you have to go through. For a common everyday silicon diode, it's going to be somewhere around 0.7 volts. It's not a lot, but it does have to happen. So it's going to conduct nothing until you reach about this value. Then it'll act more or less like a short. It's always going to have that 0.7 across it, but other than that, it's basically a short. And you have electrons flowing. If you do the opposite, if you have positive on this side and negative on this side, well, there's not enough for the there's not enough of that kind of pull to be able to do this. Now you could put a massive positive voltage here, right? You could have a massive voltage, and then you will overcome this, and you'll rip electrons from here and push them in here and all that kind of stuff, and it'll work. It won't be pretty, but it'll work. And you might, if you reverse this, you might actually get a very tiny current flow. It would be, micro or probably even nanoamps, but you might get a slight one because, these electrons might pop out of here, an electron might go in here, but you're not really going to get much more than that until you basically fry the component, which you can do. It's called you get avalanche current or something like that. I don't remember the exact term off the top of my head, but you can break it down. So I'm skipping over a lot of stuff, but this is the basic idea. Now let's talk about a transistor. A transistor is the same thing as a diode, except that apparently it's not drawn as well. That's terrible. That looks like a dumpster. I'm going to redraw that. This is less bad. Okay, there we go. It's the same idea, except that we have this P-type material and then two N-type materials. That's why what we have is an NPN transistor. There's, of course, PNP and so on, and they work similarly. So we have this. Now, what is this going to do? Well, what we want, and just to mark these off, we have the collector, the emitter, and we have the base right here, just to kind of mark off what these are. Now, we basically have two flows. I said this before, in a way. We have this is one of the ones that we care about, right? Coming from the emitter and going out through the collector. We have this flow. We've also got this flow. These are the two flows that we mostly are caring about in this case. So how does this work? Well, this is usually connected to something positive. This is connecting to something negative. Usually it's ground, some variant of ground or ground through a resistor or something. Now, you're not going to be able to pull current through this, right? We have an NP junction. Even here, you could connect this to something, you could connect this to negative or something like we have a reverse biased thing here. Here we have the correctly biased thing, right? Normally base is connected to positive. So we have negative and positive. This is going to act just like a diode. So you can, ignore this part and just see, okay, we're going to have a flow here and we'll have about 0.7 volts or whatever. It's going to depend. Our transistor, I looked up the data sheet, is, I think it was about a volt. It might have been, I'd have to look it up again. I think it's about a volt, somewhere between 0.7 and 1.2, and I think it's going to depend, but it's a small value. It's the same idea. It has to push through this wall, this junction. Once that happens, it primes the way for this guy to allow current to flow through here. What you're basically doing is you're breaking down all of this. And normally you have a smaller kind of amount of current flowing through here. So this is usually a small amount of current. This is I of B, whereas I of C is sort of much, much higher. And just how it's physically put together is going to determine how big of a boost that is, as well as other characteristics. And back to our open circuits book, we have a diode. This is just a regular diode. Here they are in circuit. This is often what they look like, a regular one. And here is what I described. Here's what I described. So we have the, the epoxy encapsulant, as they call it here, very fancy, just that outer piece, the wire coming in. We have our silicon actual chip right here. So this is the actual the PN junction thing here. Some solder here to connect it, but this is our silicon chip. The silicon fill is just the stuff around it, but this is the actual PN junction. Here it is physically. So again, there's our silicon right there. That's going to be our PN junction. You can't tell the difference between the P and the N junction. It's just doped. Here's the silicon fill, and then the two electrodes going in. And here we have a transistor. This is the 2N3904 transistor, but it's the same basic type that we have. Here it is. And here it is sliced apart. This is all just part of the sort of heating and all that stuff. Here are the wires coming in, and there's our tiny little piece right here. And back here on the bench, we're going to bring it all together. So I have 2 ammeters hooked up. This is the current from the base to the emitter. This is from the collector to the emitter. So this is the current that's going to the motor. To go back to this model, the orange meter is going to give us this current flowing in this circuit. The blue meter is going to give us this current flowing through the motor, because we have kind of 2 sub-circuits here. And you'll see that they're going to be significantly off, hopefully. And there it goes. So we have about 3.68 milliamps going through the emitter base, and we have about 114, 15-ish, 113 going through the motor itself, and the motor is freaking out. If I press the button, what that's going to do is it's going to short this out such that there's nothing going through the base to emitter. So that's going to cause the motor to stop, because now nothing's going through here, so it can't go past that NPN junction. We're going to have similar current going through here. We're going to have a slight uptick, because we're not going to have this, probably 0.7-ish drop. So I expect to see a slight uptick when I do this through that resistor. So that 3.7 I expect to go slightly up. And it did. It went to 4.5. And of course, the voltage, or the current going through the motor, is gone. So there we go. That seems quite simple, but it's the basic idea behind a transistor, how it works, and what we're going to use it for, which I'm sure is going to be building an H-bridge. We'll probably build 2 of them. I think there's going to be 4 transistors, and they'll work in concert to build this H-bridge to allow it to go. Basically, we have the same type of circuit forward and backwards. And that allows the microcontroller that I expect we'll eventually get to be able to handle the 120-ish, 110 to 120, probably more when it's under load, probably closer to 150-ish milliamps that the motors are going to need without burning out the microprocessor. If you're trying to build your own robot, especially if you're using something like an Arduino or something like that, you're really going to need to do this. You can look up the H-bridge or wait until we get there. I'm sure we're going to build one. But you're really going to want to make sure that that is set up. And that's it. So thanks for watching the technical video. I'll see you all tomorrow.